A good question about technetium. So you might notice technetium is the smallest radioactive element. It's also the smallest synthetic element. And so I don't remember if we've discussed that yet, but does anybody know what the term synthetic element means? It's not it means it's made up. It means we don't find it in nature on Earth, because that's kind of what we define as our environment, when really we probably should be looking at the solar system as a whole. But either way, we shouldn't find any technetium in the entire solar system, and it's not because technetium never occurs naturally, but technetium's most stable isotope that we've been able to find, something about the particular ratio of protons and neutrons, the most stable isotope we've been able to find only has a half-life of like, I think it's like 90,000 years, which sounds like a long time until you consider that it was last made naturally in that supernova that led to our solar system, which was 4.5 billion years ago. So basically, all the technetium that had naturally occurred in our solar system disappeared before life evolved on Earth and started looking for it. So it's not that it was never there, it's just it was gone before we looked for it. As to what it is specifically about the number of 43 protons to the number of neutrons that causes it to be more unstable, that's a good question for a second or third year physics class. Because it really has to do that. There are certain, I don't really like this term, but the physicists use this term, so I'm going to use it as well. They call them magic numbers. There are certain specific magic numbers of protons and neutrons and protons relative to neutrons that cause things to be exceptionally stable or exceptionally unstable. So with that in mind, 43 protons might just be a non-magic number, an anti-magic number, a specific number of protons that has no stable ratio of neutrons, which I'm trying to think, is 43 a prime? It might have something to do with that being a prime number, therefore you can't get the right ratio of neutrons to protons because it's a prime number. So I can't speculate much more beyond that, other than it's an inherently unstable number of protons, and that's why there was none of it around. It was also one of the first elements that they actually managed to make in a particle accelerator, mostly because they knew there was a gap there. They knew there was an empty spot where they couldn't find anything, so they started trying to smash stuff together to make it, and it's a little bit more stable than most of the radioactive elements. So that in mind, let me pull up the slides here. And we'll start by actually running the numbers on this one. Let's do a practice.
How did they get it so it matched up and they found that it was something they had?
Well, so they knew that they could find an element that had 42 protons, and they knew they could find an element that had 44 protons. So there must exist an element that has 43 protons, but they couldn't find it anywhere in nature. So if you think that something exists, but you can't find it anywhere in nature, one of the things humans do is we use technology to try and make it. So basically, they just knew that there was that empty spot. Just the same way that we had those placeholder numbers down for 113. Like we knew that there has to be some element with 113 protons. We just don't know how to make it yet until they got the exact right ratio of energy and particles and speed together. All right, so quick reminder about how we do these problems. This is one of two types of calculations that I'm going to teach you when it comes to nuclear chemistry. And question number 10 on your in-class test is going to be one of those two types. I won't tell you specifically which one. It's either going to be this or it's going to be a half-life question that we're going to go over after this. Right, so you've got a 50-50 shot of this being on the test, which is actually, all things considered, that's pretty good because these are actually relatively easy questions to solve if you know the right things to watch out for. So what's what are the things we have to watch out for with this? What's our general process here? How do we find delta M? Change in mass. So we do what?
Total minus,
So before we did total minus the parts, right? That was when we were talking about an individual nucleus. If we're talking about a reaction, the only difference is usually with reactions, when we have a delta, it's final minus initial. So you take your final amount of mass and you subtract your initial amount of mass. And that'll give you your change in mass for this reaction. And it can be a positive number. In this case, we lose mass. But if it's a reaction that actually you have to put energy in to cause it to happen, then we actually might gain mass when we go through a process. In this case, we're going to lose mass, so delta M is going to be negative, which means it's going to be an exothermic reaction. But yeah, the general process is just, well, if C squared is a constant, delta M is change in mass, so do final minus initial, and then you just plug it in. The only trick beyond that is that you have to pay attention to your units. Because the units that are given on the periodic table or on here are either AMU or grams per mole. But if we're doing a physics equation, we need to use physics units, which means we don't want it in grams per mole, we want it in kilograms per mole. So all we do is if we have a delta M in grams per mole, we're going to divide it by 1,000 to get kilograms per mole. So delta M in this case is, what do we get? We get something like 0.2, just under 0.2.
0.1848.
1848, is that what I heard? 489. Which, because of the way AMU is defined, is the same as grams per mole, right? So the way we're actually going to plug it in is just take that and put it in kilograms per mole. This is the only time we really do kilograms per mole in chemistry. Occasionally in biochemistry, because some proteins have a large enough molecular mass that they're in the tens of thousands of grams per mole. So occasionally you'll do kilograms per mole for biochemistry, but more often than not, this is the only place you see it. So that's going to be 1.8489 times 10 to the minus 4 kilograms per mole. You don't have to put it in scientific notation, but hopefully we're all comfortable enough with scientific notation and converting grams to kilograms at this point that everybody sees where this number came from. So then all we have to do to get our delta E is 1.8489 10 to the minus 4 kilograms per mole times 2.998 10 to the 8 meters per second squared. Reminder, that number is on your conversion sheet in your useful constants section. And so you don't even need to remember that. You just need to know what C is and know how to look it up. So when we plug all this in, ballpark 9 times 10 to the 16 is really close to 1 times 10 to the 17 times this number. So it's going to be something like 1.6 times 10 to the minus 10 to the positive 13 ish. And what happens with our units now? The whole point of putting it in kilograms is so that we wind up in kilograms times meters squared over seconds squared. which is the physics definition of a joule. And then nothing has to do with the mole, so we just leave the per mole on there. So again, as long as you can remember that this needs to be in kilograms, the only speed of light on your equation sheet is in meters per second already. So just remember that that winds up giving you joules per mole. Yeah.
If we left it as kilograms, your square root of seconds would be like.
Maybe half a point, because that is technically an energy unit, but it's not an energy unit that most people will recognize. So that's being nitpicky. It'd be a very minor deduction, but I wouldn't give you a perfect score if you left it as that. Because we don't want things in kilograms meters squared per second squared. Technically, it's a joule. I don't know. I have to think about that one. The better answer is to put it in joules per mole. So plug and chug, right? Once you know what the variables are and where to find them. And basically on the test, if you look at the practice test, for this type of problem, I'll give you a table. I'm not gonna set it up as products versus reactants, and I'm not gonna add everything up for you. So you have to know how to use your calculator to add things up. But you just take all of your products minus all your reactants. Then divide by 1,000, put it in kilograms. Right, so should be hoping for one of these on the test, because not only is that a pretty easy one, that's also relatively fast compared to some of the calculations we do in this class, right? This is no ice table involved, no assume x is close to 0, no stoichiometry even. Or not very much stoichiometry. Technically, getting the balanced reaction in the first place is stoichiometry, I guess, but.
There's a 50-50 chance we'll pop this on the test.
Mm-hmm. I'm glad you asked. There's another practice problem on here, and it looks really similar. This is going to be basically how I'll give it to you on the test. This one's a fusion reaction, but it's going to work the same way, products minus reactants. In this case, we start with two small things and we make helium and a neutron. Off the top of my head, I'm not sure if you have to put energy in for this one or if we get energy out. I think we get energy out. I think delta M is negative. Yeah.
Gets less.
But not really a whole lot different about this process, right? All right, the last concept. It's the idea of chemical rates, and we're going to go through some basic math concepts as they apply to chemistry pretty quickly, with the goal of getting to here's the equation that you know how that you can use. Right? In general, we haven't touched reaction rates yet. We've touched equilibrium, which is where the rate equals 0, where things stop changing. But it turns out the process of getting to equilibrium has some kind of interesting math too, because the rate of change of these reactions winds up being important in some cases. Right, so a couple definitions for starters. We say that our rate of our reaction, we measure it with respect to changing concentrations over a change in time. So if we were looking at this, if we called concentration Y and we called time X, what does that equation look like now all of a sudden? Change in Y over change in X. Does that look familiar? What does it look like? Or you might rewrite it as Y2 minus Y1 over X2 minus X1. Does that look more familiar? It's a slope, right? So basically the reaction rate is the slope of the line if you plot concentration of a product versus time. We look at concentration versus time, we'll get some function that looks like that, where it's going to be approaching equilibrium. It's going to have some asymptote that it's approaching. When it gets to the point where that's flat, that means that this slope is zero at that point, right? In other words, nothing is changing, which is kind of what we defined as equilibrium. We reach equilibrium when the concentrations stop changing, right? But what about all this section here? Basically, the reaction rate is the slope at any point along this line. Should have used a different color so it was a little easier to see what I'm showing here. But if we have some slope at any given point, it's going to be how much is your concentration changing divided by how much your time is changing. So for these radioactive elements, to get back to the radioactivity, the radioactive elements by definition are not stable. And really, they don't even really have an equilibrium where they become stable, because it's not like things are recombining to make the less stable nucleus. So we don't ever really reach an equilibrium. In that case, if we were talking about, say, uranium breaking down naturally, the graph of amount of uranium-238 or 235, we'll use that one, versus time, it's going to have some initial amount, and then it's going to gradually decrease and asymptotically approach zero. Well, that's all great, except all of the math we've done so far relies on stoichiometry and equilibrium, and this will never reach equilibrium. So how do we calculate what's going on if it's not at equilibrium? That's where rates come into play. How do we know how much uranium is left at any given time? It's based on the slope at any given point. First off, what kind of function does this look like? The first time we said exponential decay, it was 1 over x, right? For pressure versus volume. But does this have two asymptotes or just one?
Just one.
Just one, right? If we measured a certain amount of uranium initially, you could still have uranium before that, right? So we really only have the one asymptote. So it is an exponential decay. And we can show mathematically why that's the case too. Let's skip some of these. So here's a better graph. So this is for the reaction. Let's see, hydrogen turns into HI. H2 plus I2 reacts to form 2HI. Simple enough reaction. The whole point of looking at this is that just like with the ice tables, when we have a lot of things changing at the same time, right? So we can kind of measure our rate a lot of different ways. The rate of the reaction is going to be based on the rate of your hydrogen being used up or the rate of your HI forming. But at any given point, really what we're talking about is that slope. And when we have slopes, when we're talking about slopes of functions that are not just a straight line, anybody know what class that shows up in? Calculus? What do you call a slope, the function that gives you a slope in calculus? The derivative. Basically, the rate of the reaction is going to be the derivative of this function. Which sounds kind of scary, especially since this is not a calculus class and half or more of you have not had calculus yet. So what we're gonna do is we're gonna skip the scary calculus part and just get to the way that we can actually use this. I'm gonna know that this, I want you to know that this is where these rate equations come from. Is these functions of concentration versus time. And then we'll skip forward and actually start talking. This is some stuff that we get into in Gen Chem. We'll have there's a whole sixth of the class basically is about rates. About half of a quarter is how I came up with that 1/6. I'm not just making it up. No, so we still hand wave a lot of the derivation. But if you've had calculus, where the functions come from makes more sense. As it is now, we'll leave it alone. So basically, one of the questions I want you to think about is why does this slope change? If we have some starting amount of uranium and it's being used up over time, why isn't it just a straight line? Well, it looks like exponential decay, but why? The less uranium you have, the slower it's going to decay. Right? So your slope is going to be steepest at the beginning when you still have a lot of uranium. And as you lose uranium, your slope's going to lessen. The activity that we didn't wind up doing this year, but the way you can think about this is it's a little bit like if you had a big box of 6-sided dice, if you rolled them and then you took everything that came up 6 and you took it out, you have less dice every time, right? But the number of 6s that you pull out should decrease every time you roll it, right? Because you have fewer dice. You have a 1 in 6 chance of rolling a 6 for each time. But if you only have 2 dice, your odds of rolling a 6 are a lot smaller, right? But if you have 25 dice, you're almost guaranteed to get a 6, right? There's almost certainly you're going to get a 6. So the reason that these rates change is because of probability. Remember how I said everything comes back to thermodynamics and the Boltzmann distribution at some point and randomness and entropy? These reactions happen if it's what we call a bimolecular reaction. Then the reaction can only happen if these two molecules run into each other. So the more we have of these molecules, the faster the reaction is going to happen. Or the other way you can think about it is the more times the reaction happens per second or per year, or depending on what time scale we're using. And so that leads us to this idea that if we change these concentrations, our rate's going to change. And we get what's called a rate law. Again, I'm not going to have you solve these rate laws at this point, but you can, if you look at these type of reactions, you can see, okay, well, the rate of a reaction is equal to a constant times a couple concentrations. So for this particular reaction, the rate of reaction is going to be equal to a constant. We use lowercase k instead of uppercase k, because uppercase k means what? Kelvin, or as a variable, it means equilibrium constant. So lowercase k, and I just make them italicized. I make it cursive, italicized. I make it cursive just to differentiate my uppercase k's from my lowercase k's because my handwriting's so good. The main thing is that you know that this one's a lowercase k. In this case, you're going to get the rate of this reaction is going to be equal to some constant times your concentration of hydrogen times your concentration of iodine. If you double this concentration, your rate's going to double. You double this concentration, your rate's going to double. Or at least that's what it looks like. Turns out there are more complicated things that can happen. So it's not always going to be as simple as you take your reactants times their coefficients, because sometimes you have a multi-step reaction happening. Sure. And only one of those steps is what we call the rate determining step. all that to say, this is the general form of a rate law. In terms of these radioactive reactions, if it's normal radioactive decay, so if I just say, okay, uranium-235 decays as a alpha particle decay, the rate of this reaction, it can only be based on one thing because we only have one reactant, right? Again, this is an oversimplification. There are other weird things that can happen where you only have one reactant, but it still has some where it has to bump into itself for a reaction to happen. But all nuclear processes, all naturally occurring nuclear decay is going to follow the same process where we get this general form. And that leads to a function that looks like this. So your rate of your reaction, which is equal to the change in uranium over change in time. We are going to throw a negative on there because rates have to be positive and our slope is negative. So we just throw a negative in front of it. But if we basically get an expression that looks like this. This is what's called a differential equation. Let me clean it up so you can see what's going on a little bit. Where we get something where the product of your function depends on the value of the product of that function. Right? So it's the fact that as this changes, your function changes is what's called a differential equation, where you have multiple things. One thing is changing, but as this changes, it also changes that. There's a whole, that's like second year calculus. Second year in not calculus BC, but second year in university calculus. So you take differential equations after you've had a whole 3 semesters of calculus and after you've had linear algebra, and then you take differential equations as a sophomore or a junior in college. So it's basically applied calculus. And what do you do when the functions get too tricky in calculus to actually do some of the standard stuff? What we're going to do with it, again, since this isn't a calculus class, is we're basically going to solve this for time and then take an integral of it. Taking an integral is the calculus term for undoing the derivative. It's an oversimplification, but there's no math faculty in the room, so I can get away with it. My best friend is one of the math instructors at the college, and he would hate that definition. But he also teaches in the sciences, so he understands. Sometimes we have to make simplifications. What this means is if we actually want to try to solve for time, we get what's called the integrated rate law. And the integrated rate law looks like this. The concentration, actually, we'll write it in the standard form first. Concentration of uranium at any given time is equal to your initial concentration of uranium, which we indicate with that subscript O. So we call it uranium naught. Naught is the mathematical term for zero. It's basically just indicating at time 0. So your initial concentration. There's E minus K times T. So again, I'm not going to go through the process of how we get there, but it's taking this function and solving it for time gives us this. And this applies again to any radioactive process. So I'm actually going to remove uranium from this because it's a lot to keep writing and it looks more confusing than it needs to. We're just going to say N for number. So how much of an isotope you have left is equal to the amount you started with times e to the minus KT. So what happens at time equals 0? At time equals 0, this whole term turns into 0, and anything raised to the 0 is 1, right? So basically, at time equals 0, we get our initial concentration back. That's one of the ways we can double check this to see if it makes sense. What happens at time equals infinity? Mathematically, we know that time actually can't go to infinity, but mathematically, if we plugged infinity in for time, or just a really, really, really big number,
It's getting closer and closer to closer.
that means that we're getting e to the negative really, really big number, and e to the really, really tiny or really, really negative number should get closer and closer to 0. It'll asymptotically approach 0. So that all kind of tracks, right? At infinite amount of time, we shouldn't have any of our radioactive isotopes left. They should all be gone. They should all have reacted. If you shake that box of dice enough times, eventually there will be no more dice left, right? It might take a really long time to get there. Well, by really, really long time, I mean like it might take you 10 times of rolling the dice before you get to 0. But the actual process remains the same. The logic behind it remains the same. All right, so what do we do with this? Well, we like to put things into a y equals mx plus b form. So basically, we're going to solve for time or as an x value. How do we get time by itself? How do we undo that e? Take ln of both sides, right? So ln of the amount of your isotope left is equal to ln of all this, which we can use laws of logs to further simplify this. If we have ln of e to the minus kt, ln is going to cancel out that e. And we're going to get or rearranging it so that it looks more like what we're used to seeing. Negative KT plus ln of your isotope naught. Okay, is that more helpful? I guess maybe. At least natural log of your initial concentration is just going to be a number, right? That's just going to be an intercept. K is a constant depending on what your radioisotope is. That has to do with how likely is it to decay at any given time. So one of the ways you can also think of it as the probability that any given nucleus will decay at any given time. In our dice analogy, it'd be 1/6. And we can do a little bit more to rearrange this, but basically this is going to give us a function where if we have a set amount of time, if we know K and we have a time, we can figure out how much of a radioisotope is left. Right? What is the normal way to talk about how stable these radioisotopes are, how long they last? Half-life. What is a half-life?
The time it takes for it to be for the population to split.
It's the amount of time it takes it to get half of what you started with. And for these first order processes, for these natural log based functions, it's a constant. Meaning if it takes let's call that one. Let's say that that's 10 years. If it takes 10 years, it's not perfectly to scale, to get to half of what you started with, how much is going to be left after 20 years? Half of a half. So at 20 years, we get a quarter. So 0.5, 0.25. And then after another 10 years, it's half of that. So if we're trying to figure out how much of something is going to be left, this is actually the function that works the best, but we don't actually look up values in terms of K. For specific isotopes, we report it in terms of half-life. So how can we actually solve for that then? How can we solve for half-life?
Add and 0.5
Not K.
or the or N.
If we set N not as 1 and N is 0.5, as long as we know K, we can solve for the half-life, or the other way around. If we know the half-life, we can solve for K. And we can also use laws of logs to combine these two terms and to rewrite this as a fraction. So basically, what percentage is left is equal to minus KT. Well, that means that this is going to be 0.5 at a half-life, right? So let's do this for uranium. Uranium-235 has a half-life of 4.5 billion years. The way we write this is T1/2. That's the way we write half-life. Times 10 to the 9 years, right? 10 to the 6, yeah, 10 to the 9. So how do we solve for K then? If concentration not is 1, this is 0.5, we just get ln of 0.5 equals minus K times the half-life, which in this case we have a number for. 4.5 times 10 to the 9 years. So natural log of 0.5 is this is a common enough calculation. I happen to know that one off the top of my head. It's negative 0.693. So negative 0.693 equals negative K times the half-life. Negatives will cancel out. So K is just 0.693 over 4.5 times 10 to the positive 9 years. Or the other way we can write that is just the general form. Does this number change depending on what the isotope is? That negative 0.693 that we then canceled out the negative, that's the same for everything if we're talking about a half-life. All radioactive processes have that same constant on top. So we can just say K is equal to 0.693 over the half-life. So now with that in mind, if we have either K or the half-life, we can go back and we can calculate how much of a radioisotope is left at any given time. We haven't been measuring the concentration of uranium-235 for 4.5 billion years, obviously. And yet we can still measure that half-life because we can measure the rate constant. So we can actually go backwards. This is usually how we get the half-lives in the first place. We can say, okay, well, we know it's a first order process because when we plot it, we get that exponential decay. And as long as we know what the slope of that exponential decay is, we can figure out the half-life. All right, let me skip forward on the slides. We don't need all of the background. Here's another example. Let's talk about carbon dating. Does anybody know what carbon dating is? How much carbon, figure out how old something is based on how much carbon-14 is in it. So for carbon-14 is naturally produced in the upper atmosphere, like I mentioned the other day. And so there's a relatively constant amount of carbon-14 in the atmosphere, in the form of atmospheric CO2. Well, if the atmospheric CO2 has a certain level of carbon-14 in it, what uses up atmospheric CO2 naturally? Plants, photosynthesis, right? Photosynthesis takes atmospheric CO2 and turns it into sugar, right? That's the whole point of photosynthesis, which then can be used to make ATP and everything else, right? Well, where does all of the energy that humans use, or anything that doesn't photosynthesize, where do we get our sugar? Glucose from where? And where does the sugar in those foods come from? Plants, photosynthesis. So everything that's living has a relatively constant amount of carbon-14 because carbon-14 is breaking down in your body, but you're constantly eating more of it. And plants are constantly incorporating more of it. So everything alive has carbon-14 in it. So with that in mind, what happens when are you going to start decreasing the amount of carbon-14 in your body?
No more eating.
Once you either cease photosynthesizing, for those of us that photosynthesize, or you cease eating things that photosynthesize. In other words, once you die. So basically, carbon-14 dating is only useful for a pretty small subset of artifacts, but basically anything. What is something that we might find in an archaeological dig site that we could date? No, bones don't have much carbon in them, but any sort of tissue. What else could we date? What else is made from things that were once living? Artifacts? Could we date clay? Clay, for the most part, doesn't have much carbon content in it, right? And a lot of the carbon content it does have might come from carbonates that were already minerals. So nothing that's made out of a mineral could be carbon dated. But what is made out of something that was once living? Yes. But in dig sites, really textiles. Textiles are one of the most, good job, Bianca. Plants, yeah. So any food scraps for starters, and even something that has been, hunter-gatherer societies or even early agricultural societies generally had what they call a midden heap, which is basically just a hole in the ground where they threw their trash. Those are actually really, really useful for archaeologists because there's almost always some leftover food that's decaying in there, or like the scraps from when they prepared their food, or there's old thread or cloth, things like that tend to be preserved in there. And so, and once societies started living in the same area for an extended period of time, you can actually go backwards in their history based on their midden heap. Say, okay, at this point, they were eating mostly this. And we can say it was this old. And then 500 years earlier, they were eating that. So they transitioned from one food source to another food source over 500 years. And we know that it's 500 years because we can look at the amount of carbon-14 in those scraps. So it's not a perfect tool. It has its limitations. But for anything that was once living, up to a point, up to the point where we get so close to that asymptote, so that we can't really tell. Eventually, what's going to happen is we get really close to 0 carbon-14 left, and our slope gets smaller and smaller too, right? So once we get into this region, we basically can't use carbon-14 dating anymore. So there is like a threshold. It's for carbon-14, I believe it's around 10 half-lives. But 10 half-lives, if a half-life is 5,730 years, 10 half-lives takes us back 50,000 years. Not a whole lot of societies were doing much before 50,000 years ago. Then you're starting to get in more back into hunter-gatherers. I think the best estimate I've seen for the invention of agriculture, which a lot of anthropologists say is sort of like the start of settled society, was about 15,000 years ago. Maybe as many as 30,000 years ago, depending on who you talk to. But that still means that carbon-14 dating covers a pretty broad swath of human history. Of course, there's the 220,000 years before that, where we were technically human and living in social groups, but not settled, when we were just hunter-gatherers, that we can't really use carbon dating for. But anyway, so if we know the half-life for carbon-14, what's the rate constant? Well, 0.693 over 5,730 equals K, or equals K. So this is the same function that's shown up there, just with the K and the T swapped. Solve for the half-life versus solve for K. So what do we get for a value for K?
1.209 times 10.
What are our units?
Whatever.
1 over years.
Years minus
Years to the -1. So 1 over years is a weird unit, but basically you can think of it as is the probability of a disintegration in a year. If you had a carbon-14 nucleus, what are the odds that it decays in a year? So once we have K, now we can actually do carbon dating. We started with 0.110 grams of carbon-14. How much will be left over after 10,000 years? Well, now we just go to the other form here. The only thing that's different, it's the same equation. It's just that once we have K, we don't have to plug in 0.5 for our ratio. And in this case, we want to plug in our initial amount and solve for our final amount. So natural log of carbon-14 over 0.110 grams equals negative 1.209 10 to the -4 inverse years times 1.12 times 10 to the 4 years. Well, that's just arithmetic, right? We can simplify that. And we're going to wind up with our units canceling out. So we have years here, 1 over years there. When we multiply them, they go away. Get a unitless number. We're going to get something really close to 1, right? -1. Natural log of carbon 14 over 0.110 grams equals, what is it with 3 sig figs? Negative.
Yeah.
Thank you. All right, so then how do we solve that for? That's the variable we're solving for, right? We want to know how much is left.
Multiply by. Oh,
E to the power of both sides. Right, e to the power of both sides is going to cancel out the natural log on this side, and then it just turns us into a number over here. What is e to the minus 1.35? 3.87? So even if we didn't have a starting amount, that's the percentage that's left. About 26% of it is left over. So we're just going to take our starting amount and we multiply by that, right? And then we're solved for it. So the total amount of carbon 14 is equal to 0.258 times 0.110, 0.028. What is it?
0.028.
What are our units on it now?
Whatever.
This is unitless, but then we multiplied by grams. So we're in grams now. Tasni?
Oh, no, I was just asking for a multiplier.
Multiply. So 2 notes about units. Really, it's 1 note about unit. As long as you're consistent, you can use whatever units you want. We plugged in years for our time because our half-life was in years. Our half-life was in years, therefore our rate constant was in years, was in 1 over years. So as long as you're using the same unit, you can use any time unit you want. You just have to make sure it's the same at all points. And same for your amounts. This works if you're in grams. This works if you're in moles. This works if you're in molarity. Works if you're in parts per million. As long as you're using the same number for amounts, this will work. Right, so because we measured our initial amount in grams, we get our final answer in grams. Make sense? Ish? All right, so this is the other possible calculation I might ask you to do on number 10. So it's not a true wild card. It's a wild card in, but with only 2 choices. It's either going to be E equals MC squared, or it's going to be this. And I believe those 2 equations are on the equation sheet, but if they're not, tell me and I'll make sure they're included. And really, it's the same equation twice, right?
Yeah.
Yeah.
So always ln 0.5.
If we're talking about half-life, yes.
Okay. I'm not talking about half-life. Is that even gonna be on that final? Okay.
I'm not even sure if you could do like a quarter life. If the quarter life. I'm not sure mathematically if that works out. I think it does, or like a 10th life. Quarter life might work because it's really just two half-lives, but I'm not sure if you could do another. I would actually have to look at the math to see if you could do that. It's always done in half-life, so don't need to worry about it.
Okay.
So this is one form of the equation. Natural log of 0.5 is equal to minus k times half-life. All right, so that's the last new material that you're gonna have on your test. Should we do another practice one?
Sure.
Instead of figuring out how much is left over after a set time, nobody's actually been measuring the carbon-14 for 10,000 years, right? But what we can do. That's plutonium example. That's what we're just talking about. Here we go. If you have a half-life of carbon-14 and you have a starting amount of carbon-14 in form of a ratio. Who here's heard of the Shroud of Turin? What is it?
Supposedly it's what Jesus is wearing.
Yeah, it's sort of, it depends on the exact story, but it's a relic from the early days of Christianity that was supposedly either something Jesus was wearing, or was used to wrap his body when he was buried, depending on which story you're asking about. It's a religious relic that was found during the Crusades. How do we know it was found during the Crusades? Well, that's when we start seeing mentions of it show up in ancient, in medieval texts and writings. So we can actually see if that's reasonable. These are all real numbers. This was a really big deal in the 90s when they first were allowed. I don't remember if it was the Vatican or that owns the Shroud of Turin, or if it's a Orthodox church. The Eastern Orthodox is really big into religious relics as well. But basically, the first time they allowed this textile to be tested was in the early 90s. And these are the real numbers. So if we have a half-life, we can come up with K, right? This is a slightly different half-life. This is a more accurate half-life. I think the old one was a little bit old. So let's go through the process of finding that the K value again. Divided by the half-life, so 5,715 years.
(1.21 time and negative and
Inverse years. Is that the same number within sig figs as the one I just erased, or is it a little bit off?
it was 1.209. We did 4.2.
Okay. We kept an extra sig fig, but really close. So if we know that, and we know natural log of n over n naught equals minus kt. Now we have k, we have n, and we have n naught. They look like weird units. Ratio of carbon-14 to carbon-12 in the upper atmosphere. Technically, that ratio is an amount, right? So we can plug it in for n. So which one goes on top? Current. Our original is the 1.0 times 10 to the minus 12. (9.19) times 10 to the minus 13 equals minus KT. We have K now. We can actually simplify this a little bit. It's going to be natural log of 0.919 equals minus 1.21 times 10 minus 4. Solve for T. This one's even easier because we don't even have to do anything when it comes to, we don't have to do e to the power of anything to cancel out logs. We can just turn this log term into a number, and then it's just regular algebra. The only tricky thing about these really is those log terms, right? Because laws of logs get a little bit messy. They're a little bit counterintuitive sometimes, unless you're living in that world. But it's been a really long time since I took a math class that had logs in it. So I remember being confused by that. So what do we get for an answer? What's time? Should be something around the 600 to 1,000 range, if I'm remembering correctly. This is inverse years. Don't second guess yourself. If you have an answer, let me hear it.
Syntax error.
698. Syntax error.
How, equation there, do ln of 0.9.
Yeah. You might have to, depending on how you're typing it in, you might have to open parentheses, but usually when you hit the ln button, it opens parentheses for you.
Yeah, I get a negative one.
But there's a negative right here as well.
Negative 0.08.
Negative 0.08.
Find out. Oh.
So that's our answer here. This is our artifact's predicted age. It's about 700 years old. Which, if you read your medieval European and Middle Eastern history, kind of makes sense. Because this was the time period about 700 years ago when the Crusades were happening. And all sorts of holy artifacts were discovered or recovered by the Europeans, but they were just kind of grabbing stuff and saying it was one thing. It was undoubtedly an important textile to a group of people, but the math and the science doesn't bear out that it was 2,000 years old.
What basis for getting Jesus?
There's kind of a weird face. Look, if you look at it, it's kind of like one of those. This is a coffee stain that looks like Jesus. It was probably used as a funeral wrapping for someone. But then 700 years ago, right, and then was taken off of that burial, and then brought back to Europe and claims to be. There's a lot of stuff like the finger bone of Saint Ignatius and things like that that kind of showed up around the Crusades, where they would just raid another culture's temple, find something in a box that looked important, and say, well, this is now that, and bring it back to Europe. And much like the British did during the Age of Sail. Oh, that's a cool obelisk in Egypt. We might as well just put that on a ship and bring it back to London, because of course London needs obelisks. That said, I'm also not a religious scholar, so if you look up more information on this and get different answers, that's entirely possible, but these are real numbers. When back in the 90s, when they first did this was groundbreaking and very controversial in that in some ways kind of led to some of the schism between religion and science started. It really got kicked into overdrive in the early 90s with stuff like this, because rather than go the more contextual approach, some religions kind of doubled down on the literalism approach and said that the science was wrong. Which that's a whole separate issue, and I'm not going to touch that. But carbon dating works. Should probably just choose a less controversial example, but I like real world examples. This is also how we date older samples as well, but we can't use carbon-14 dating once we get past about 50,000 years, and so we have to start using other isotopes. And so that's when we start using geological samples. When we start getting into dating the age of a rock, we're going to have to use other isotopes. And that's how we also do things like I mentioned, like dating the solar system. We use the ratio of uranium-235 in a sample of rock relative to the ratio of lead. We don't necessarily know what the initial amount of uranium was, but if we know a particular mineral when it was formed had no lead in it, which we can tell by looking at the geology and the crystal structure, if we can say, okay, well, initially it was all uranium-238. And now it's got some ratio of uranium-238 to lead of a specific isotope. Then we can say, okay, well, we can date that rock, or at least we can date that when it coalesced into that mineral based on that ratio of lead to uranium. And then that still kind of opens itself up to like, well, what do we do? Like, how do we know that that's true? There are other processes that we can use that basically that agree with it. So potassium in particular, yes, it is.
Yeah. I don't have a.
All right. This also leads to particularly tricky word problems. They're not really tricky word problems, but word problems we have to pay attention. Because if we have something that involves masses of two different elements, we actually have to go back and do some atomic mass calculations and convert grams of lead and grams of uranium to moles of those, because we know it's a 1-to-1 ratio for moles for lead-206 to uranium-238. But because they don't have the same molecular weight, we have to be careful plugging those in. But this is more in depth than what I might ask on the test. What I might ask on the test be something like this. Plutonium-236 is an alpha emitter with a half-life of 2.86 years. Sample initially contains this much plutonium. How much is left after 5 years? Same process. From the half-life, get K. From K, get your final amount. The only way I might switch it up is give you a current amount and ask you to work backwards. How much was present 500 years ago? If this is your current number. Ready?
Is it 0.69 for the value only for carbon-14?
No, so this is only for carbon-14. The half-life, this is natural log of 0.5 with the negative sign canceled out. Okay, so natural log of 0.5 is negative 0.693. So if you take that function and you cancel out the negatives, you get that. So this is for everything as long as we're talking about half-lives. Time. So once we have K, we can solve for a time if we have these two values. This is just that function. So natural log of your amount over your initial amount equals negative K times the time. depending on what units are on K, that'll tell you what units you're using for time. Because sometimes we're not dealing in years. Some of these radioactive isotopes have half-lives that are measured in the seconds. If that's the case, then that just means you're gonna plug your time in seconds.
Always, current time over initial time.
Current amount over initial amount.
Current amount.
Right, and the initial amount is the amount at time equals 0.
Yeah. Over.
All right. Let's end the last lecture by talking about nuclear bombs again. Here's a better drawing than what I drew on the board the other day. This was the engineering that went into the first bomb. That was the one that was dropped in Los Alamos or for the Trinity test, as well as the bomb that was dropped on Hiroshima. It's basically you take a big chunk of uranium and you take a smaller chunk of uranium and you slam them together using conventional explosives, and that takes you over that critical mass. Once you get over that critical mass, you get a chain reaction happening. So a chain reaction looks like uranium-235 plus a neutron splits up into these other pieces plus 3 more neutrons. Each of those neutrons can run into another uranium-235. And so you wind up with an exponential growth. Every time this reaction happens, it starts 3 more reactions.
Until they're all the uranium gone.
It'll go until all the uranium's gone, but what'll happen before that is that it releases so much energy so quickly that it vaporizes everything within a couple miles. Not a couple miles for this size, but it basically you wind up with like a uranium mist all over everything because it just turns the uranium into a vapor, the remaining uranium into a vapor. That then gets dispersed over the area. Plus, it doesn't help that this barium isotope is also radioactive. And plus, this isn't the only reaction that happens. You also wind up with a bunch of other side reactions that can kind of happen. And then if you wanted to get more creative with it, which is, let's be real, when humanity finds a new weapon, the first thing they do is, well, how can we make it more explosive or more deadly? How do we get better use of it? So one of the things they did was they switched out uranium for plutonium, but then they also switched it to what's called an implosion style bomb, which is basically instead of having 2 pieces of uranium that get slammed together at high speeds, what if we had like 8 pieces of plutonium that all got shot together at the same time? Then we can get a much larger yield because instead of being limited to about 2 times the critical mass, we can go up to about 8 times the critical mass. If every piece of plutonium is 0.9 times the critical mass, we get a lot more plutonium slammed together and therefore a lot bigger explosion. The reason that they didn't do this for the initial trial and for the first bomb was basically it was seen as being a lot riskier because all the engineering that goes into this is a lot trickier to get these shaped charges all pointed at the same point so that all of your slugs of plutonium hit the same point in space at the same time is a lot easier than shooting 1 bullet at a target. It's like shooting 8 bullets at the same target and hoping they all hit at the same time. Obviously, they were able to make it work pretty well, and then they upgraded that. So the first one, and basically because they slammed, they're actually able to do it with less than the critical mass because they compacted everything so tightly. Then the next thing they did was turn that into making a fusion bomb. So a fusion bomb is exactly what it sounds like. Instead of using fission, it uses fusion reactions, but in order to kickstart the fusion reaction, they actually had to use regular nuclear weapons. So you start with a uranium explosion that compacts the smaller nuclei to the point where they start a fusion reaction. And when you do that, you get the largest bombs ever made. So the little boy and fat man were measured in the kilotons, and 10 kilotons and 15 kilotons, I think. Tsar Bomba is the largest bomb ever detonated. Tsar Bomba, King Bomb in Russian. Was 50 megatons. So more than 50 times larger. Sorry, no, more than 1,000 times larger than the bombs that were dropped on Hiroshima and Nagasaki. Then there's that link to that nuclear map, Michaela. It's hard. I'm sure somebody has a number somewhere. I don't know off the top of my head. I know that they've worked on decommissioning a lot of them, but still more than enough to kill every person on the planet several times over. I think we're down from the height of the Cold War where it was enough to kill every person on the planet like 200 times over. Maybe we're down to maybe like 10 times over now. Yeah, it's baby steps, right?
About 12,000.
12,000 nukes left.
Because you know, after the first 100 times, they'll have learned their lesson.
Yeah. And all right, last point I want to make. This dude right here, Edward Teller, is a perfect example of why just because you're smart and a good engineer, you shouldn't necessarily be trusted to make decisions for the entire planet. Because he was of the opinion that we should use hydrogen bombs to dig harbors in Alaska. He wanted to put one into the ground in Alaska and blow it up just because it was easier than digging out a harbor. Yeah.
Basically, we're just bombing the land.
Yeah. He basically because he designed it, he was of the opinion it couldn't be bad. There had to be some positive use for it, or else how does he justify his life's work? And so he's like, oh, we want to know what the moon's made out of. Let's launch a hydrogen bomb at it. We want to dig a harbor somewhere. Let's just blow it up. The dude was wild. Read about Edward Teller if you're interested.
There has to be a reason, right?